Also today, this morning, or this evening, depends on which time zone you are. It's a great pleasure to have Dr. Colin Jackson speaking in our seminar to kick off our 2021 seminar series at Zhejiang University. So Colin Jackson got his PhD from Brown University and then did his postdocs in Washington, D.C., first at the Geophysical Laboratory at the Current Institution for Science, and then at Smithsonian. And before he studied as assistant professor at Tulane University. So Colin's interest has always, I could say that always on the volatiles. It depends on what type of volatiles we're talking about. A lot of the previous work that impressed us about the different noble gases. But today he's going to talk about another volatile, nitrogen. That was the work that mainly he did when he, at the time when he was at Smithsonian. So with that, I'll give it the rest time to Colin. And we are quite a casual seminar. So it's like semi-formal, like chatting with your friends. So people will type their question in the chat, but later on we could have more discussion. So we're more flexible in terms of the format. Okay. Okay, I will leave a time for you, Colin.
Okay, well, yeah, thank you very much for the invitation to present in the seminar. Is this line on my screen or is that on your screen? This V, do you see it?
Actually, I could see it. I don't know how to erase it.
Is it my? Well, let's see if we. I don't recall putting it on the screen.
No, I think that's probably somebody else that.
I can clear it.
Could we erase it?
There it is. Okay, yeah.
Okay, perfect. Okay, there you go.
Okay, well, without further ado, yeah, thank you very much for the invitation to present in the seminar, and I guess maybe this is one of the silver linings to the to COVID, that we have the kind of opportunity now to have more vigorous international communications via these types of platforms. So this is at least one benefit of the situation we are in. The central focus of the presentation today will just be an attempt to answer this question: how does Earth maintain a nitrogen-rich atmosphere over its prolonged geological evolution? This is a collaborative project I completed with Liz Cottrell and Ben Andrews, both of which are at the Smithsonian Institution in Washington, D.C., here in the States. Okay, there we go. So why is nitrogen important? Why is our nitrogen-rich atmosphere important in maybe the most general ways? At first, I would emphasize its importance to life. All the proteins in your body need nitrogen for their function. And that nitrogen in your body was ultimately sourced from the atmosphere, where life broke the triple bond of the N2 molecule, investing a lot of energy in that process to make the nitrogen bioavailable to be incorporated into organisms. So that large amount of energy that's dedicated to life incorporating nitrogen into its structures is one very clear piece of evidence for how essential nitrogen is for life and its functions. The stability of oceans, nitrogen being the major pressure component of the atmosphere, allows for our oceans to be stable over a much wider temperature range than if we didn't have any nitrogen within the atmosphere. So kind of the oceans of our planet, their stability at least is related in large part to nitrogen. And then also maybe lesser appreciated would be pressure broadening. So again, nitrogen as a major pressure component of the atmosphere distorts greenhouse gases within the atmosphere, and that distortion makes those gases more effective at trapping heat. So nitrogen in an indirect way also contributes to the greenhouse effect that keeps our planet, that drives our planet's climate through time. So the punchline to our to this talk is this simply given here by the title of the paper is kind of the basis for this talk as well, and it's this: warm and oxidizing slabs limit the in-gassing efficiency of nitrogen to the mantle. So we think that slabs which are warm and oxidizing will be crucial in maintaining a high partial pressure of nitrogen in the atmosphere, and hopefully I can convince you of that point over the next hour or so. So to put this into a cartoon framework, we can introduce this slide where we have a relatively volatile-rich slab at Earth's surface containing large amounts of carbon, hydrogen, argon, nitrogen being input into a subduction zone. And as that slab descends into Earth's interior, it experiences higher pressures and higher temperatures. And with those higher temperatures and pressures, dehydration reactions are forced. and fluids are produced, and those fluids exit the slab and ultimately are returned back to Earth's surface via arc processes. Less reactive volatiles, such as argon or N2, will likely partition into that fluid and be returned back to Earth's surface efficiently, whereas more reactive volatiles, such as more reactive volatile species, such as hydroxyl or carbonate groups or the ammonium ion, can dissolve within minerals, and therefore, despite fluid loss from the slab, volatiles that have speciations like this can be retained in the slab and then ultimately returned to Earth's interior, to the Moore mantle, following this green path. So we have this bifurcation of less reactive volatiles going back to the surface and more reactive volatiles being held within the plate, re-enriching the planet in its more volatile components. To give some numbers for nitrogen, we have about 4 × 10 to the 21 grams of nitrogen at our surface, concentrated primarily in the atmosphere. And then the subductions on flux, we think every year we subduct about 9 × 10 to the 11 grams of nitrogen through processes like this. And so if you just simply multiply this flux by the age of the Earth, that would predict that if we have 100% efficient transport of nitrogen from the top of the slab or from the top of the subduction zone into Earth's interior, that essentially that the PN2 for Earth should go to 0 after 4.5 billion years of subduction. 100% of Earth's atmospheric nitrogen should have been brought back into Earth's interior via subduction, just with the modern day flux and this assumption of 100% efficiency of transport into the mantle, essentially saying that this blue path does not exist for nitrogen. The net nitrogen goes from the red or from the black path to the green path back into Earth's interior. But we actually do have constraints on how PN2 for Earth's atmosphere has changed through time, and those constraints are given on this plot. This is PN2 versus age. So this is the start of the solar system, and this is the modern day here on the left. And our earliest constraints come from the chemistry of fluid inclusions trapped in hydrothermal quartz. It gives an upper limit and a lower limit very similar to the modern day value of 0.8. Going a little bit forward in time, we have the diameter of raindrop imprints, which we can use those diameters to back out the thickness of the atmosphere and therefore the pressure of the atmosphere in general. And that suggests maybe a slightly thinner atmosphere at 2.7 compared to the modern day. This is the upper limit and this is the lower limit according to that raindrop analysis. Going a little bit closer to modern day, we have the nitrogen-carbon ratios of organic material, which can be used to derive a constraint on the nitrogen partial pressure, suggesting a value very similar to modern. And then going to the modern day, clearly we have direct measurements of the atmosphere. And so despite this large flux of nitrogen into subduction zones and the potential drawdown of the atmosphere into Earth's interior for nitrogen via subduction, we actually don't see any large-scale changes in PN2 through time. So we don't see a decrease in PN2 associated with subduction. If anything, from 2.7 to the modern, we might even have a small increase in PN2, suggesting Earth is actually in a net outgassing state for nitrogen despite that subduction flux. So just to emphasize that what these types of observations suggest is that most of the nitrogen that is subducted will be returned back to Earth's surface via various arc processes, either arc magmatism or fluids fluxing through the back arc or the fore arc. We can then place nitrogen into a larger context, comparing its distribution to other volatile elements. So this is a plot of the abundance of nitrogen in Earth's exosphere reservoirs. The exosphere is the atmospheres, the oceans, and the crust summed together, then normalized to the abundance of nitrogen, or these different volatiles, in the Moore mantle. So it's kind of the surface enrichment relative to the interior enrichment of these different volatiles. What we can see is that for argon, which is a noble volatile, so it has no propensity essentially to form chemical bonds, so it's a noble element, a noble gas. It's highly enriched at Earth's surface, a factor of 1,000 enrichment in the exosphere relative to Moore mantle. Whereas these more reactive elements, elements that have more reactive species associated with them, carbon and hydrogen, have distributions which are much closer to equal. Here in log space, a value of 0 would be an equal distribution of carbon and hydrogen between Earth's surface reservoirs and the Moore mantle. So the question is, where does nitrogen plot? The star of our story here. Nitrogen plots in this intermediate position between kind of a pure noble gas, argon, and these more reactive elements, carbon and hydrogen. So why does nitrogen have this intermediate position in this space? I would argue it's a reflection of the various species and their stability, I guess, within subducting plates, and plates which are losing fluids. Nitrogen may speciate as the N2 molecule, which or the ammonia molecule. And these are essentially, they're going to be noble species because they have their requirements for kind of electrons satisfied internally. They don't have any propensity to form additional chemical bonds. They're neutral species, just like argon is. And so as these species become more stable within subduction zones for nitrogen, that would drive nitrogen's position in this space upwards. Or as the ammonium ion is another potential species for nitrogen, and because the ammonium ion is a charged species, it forms chemical bonds, is able to dissolve into minerals. And so as the ammonium ion becomes more stable, that would actually drive the position of nitrogen downwards in this space. It's important to stress that on this ammonium ion, it's a single positive charge, just like potassium. It has a similar ionic radius as potassium. And so it substitutes readily into minerals that have stoichiometric potassium associated with them, such as feldspars, but more importantly would be micas. Micas appear to be the phase within subducting slabs that have the highest propensity to incorporate this form of nitrogen. So micas, as a general class of minerals, appear to be very important for holding on to nitrogen within subducting systems. Okay, so let's now kind of try to understand a little bit more about what controls the stability of these different species of nitrogen. This is just a reaction that converts N2, so this noble form of nitrogen, to this reactive form of nitrogen. We can see just from the stoichiometry of the reaction that under more reducing conditions, this O2 value will be low. And from kind of a Le Chatelier analysis, if this value is low, then the stability of the ammonium ion with respect to N2 will increase. We'll stabilize this reactive form. We also have protons in this reaction, which indicates that pH will be a controlling factor for the stability of the ammonium ion with respect to the N2 molecule. And what we see is that for higher for higher proton activities, for more acidic conditions, that also will stabilize the ammonium ion over the N2 molecule. And then to kind of bring the ammonium ion, to bring the ammonia molecule into the talk, or back into the talk, it had this reaction here where we can then protonate the ammonia molecule to create the ammonium ion. And what this reaction demonstrates is that under more basic conditions, when this value is low, then that will preferentially stabilize the ammonia molecule over the ammonium ion. So we think that under reducing in basic conditions, that will stabilize this less reactive form of nitrogen. So we actually have a very rich geochemistry. We have redox and we have pH that modulate the relative stability of these different nitrogen species. And then just like every other chemical reaction, the stability then of products versus reactants will also be a function of pressure and temperature. And therefore the speciation of nitrogen within subducting systems will also be a function of pressure and temperature as well. Okay, so what we've established then is that Earth's geological history has maintained nitrogen enriched at Earth's surface despite a relatively large subduction flux. And this suggests that as slabs are subducted into Earth's interior, there is efficient loss of that nitrogen from that slab so that the nitrogen can remain within the atmosphere over geologic time. And so the goal then of this study is to react slab analog materials under the pressure temperature composition conditions, that's what PTX stands for, to simulate that process in the lab of nitrogen equilibrating within a slab system to identify the conditions, the PTX conditions, that promote efficient loss of nitrogen from the slab. So we can understand how we can maintain a nitrogen-rich atmosphere over the billion-year timescale. Okay, so step one in this goal is to seal a synthetic slab sediment, a peelite in composition, into a platinum capsule that contains or is doped with some amount of nitrogen. We use either ammonium nitrate or ammonium chloride as our dopant for nitrogen. So we have a chemical system that contains some known concentration of nitrogen that mimics what a slab has for its chemistry. So this is kind of the first step in our experimental method, but it's important to emphasize that that the speciation that nitrogen has within the chemical system is also going to be a function of the redox state of the system. The ammonium ion is a reduced form of nitrogen, whereas N2 is an oxidized form of nitrogen. So we think the chemical reactivity of nitrogen should also be a function of what we call the FO2 of the system, or really the redox potential of slabs. So to control for FO2, or the redox potential of our experiment, we then kind of go to our second step, where we load our platinum capsule into a gold adder capsule along with water, H2O, and a metal oxide buffer. So let me now show what this looks like in a cartoon cross-section formulation. So this is our gold adder capsule, and this is our platinum inner capsule. And these circles here represent nickel metal and nickel oxide, gray and green phases. So within the adder capsule, we have the equilibrium between nickel metal and nickel oxide for the pressure and temperature that we run our experiment at. And if this potential is fixed, or if this component is fixed in the reaction, and this component is fixed in the reaction, then that requires then that that this potential for oxygen is also fixed in this portion of our experiment, this outer area. So we can use the equilibrium of a metal and its oxide component to fix the oxygen potential, or the redox potential, in this area of our experiment. We also have loaded, recall, water into this outer section of our experiment. And if this potential, so if we have a fixed potential of water in our experiment, we also have a fixed potential of oxygen in our experiment, then that must fix then the potential of H2 as well. So we have kind of these coupled chemical reactions that all are operating in the outer portion of our double capsule experiment. And what this allows us to do then is that H2 is permeable through hydrogen. So then this potential for H2 fluxes across our platinum intercapsule barrier, and then that basically equilibrates the potential of H2 between the outer capsule and the inner capsule. And because then we have this fixed potential of hydrogen in our inner capsule, and our inner capsule is also water saturated. So if this is fixed and this is fixed, then the oxygen fugacity, or the redox potential of our inner capsule, is also fixed as well. So that's a lot of words to explain a double capsule approach, but this is what allows us to control for the redox potential in our experiments, which allows us then to understand how redox conditions affect the reactivity of nitrogen with silicates under controlled conditions. Okay, so we have our capsule, and X is completely controlled. We have the sediment chemistry loaded in, we have our nitrogen loaded into our capsule, and we're controlling for the redox state of our experiment too. So X is completely controlled, and now we want to control the pressure and temperature of our experiment too. So we take our capsule, and then we load it into what we call a piston cylinder press. And this is just what the piston cylinder looks like at Tulane University. This is actually a picture of my lab. I'm not going to go through all the steps of running an experiment in the piston cylinder, but basically we can take this material, load it into this press, and that subjects this capsule to fixed pressure and fixed temperature over long run durations. Okay, so this is what the piston cylinder press looks like when it's actually operating. This is our temperature control. So this allows us to both monitor for temperature and also then modulate how much power basically is being, flowed through the press, which allows us to then to control for temperature too. So we have the ability to monitor and control for temperature with this box. And here are different pressure gauges, which allows us also to have an active measurement of the pressures that are being generated inside the press. In this region right here, We have different cooling hoses to keep things from overheating. And then this is Jerison, who's an undergraduate intern working in my lab too. I guess we have a green light, which means that the experiment is running as planned. So Jerison is giving us the thumbs up, I guess, optimistic that the experiment will run to completion in a successful way. So at the end of the experiment, well, what we do is we quench it, which is just going to be turning the power off. So we then go from high temperature to low temperature very rapidly. And then we can then leak the pressure of the press back into this pump here. And that allows us then to recover materials from high pressure back to the ambient pressures of the lab. Okay, so this is what now an experiment looks like in cross-section. After we've decompressed the experiment, recovered the experiment, put it into epoxy and polished it to a cross-section to kind of expose, rather than the cartoon diagram that I showed before, this is now a real image of what our experiment looks like in cross-section. So this is the gold adder capsule. It's actually now being compressed kind of in response to the pressures that we applied to it. And this is our platinum inner capsule. And this this more milky phase here, this kind of whitish phase, is a quenched magma. And then you can see kind of ringing this quenched magma are a variety of different mineral phases. And those are the minerals that we reacted under controlled pressures and temperatures and prolonged durations. And then away from this magma and these minerals is actually void space within our platinum capsule. And that represents the location within the capsule which contained the hydrous fluid that we also reacted with the magma and the minerals under high pressures and temperatures. Okay, so this is the basic geometry of the run products of our experiments. And this is just zooming in with photons to start. So, or yeah, just zooming in with photons. So there's just a higher magnification of that region with the different phases present. And now this is zooming in with electrons. So putting our experiment within an electron microprobe and then using electrons to image our sample. This darker gray phase is the quenched magma. It actually vesiculates upon quench a little bit. So these little circles here are bubbles that formed within the magma upon quench. And these different lighter gray phases are the different minerals that reacted within our experiment with the magma and the surrounding fluid. And then this this black region here, that's the void space within our experiment, which represents the location of the fluid of the experiment. So basically, this gives you like a microscopic image of what the experiments look like after we get them within an electron microprobe. So because we're imaging our samples with electrons, that also allows us to do X-ray spectroscopy on our sample on the micron scale using an electron microprobe. And with that electron, or with the X-ray spectroscopy, we can then quantify the distribution of nitrogen between these different phases. We can measure the concentration of nitrogen in the magma, and then we can measure the concentration of nitrogen in the different mineral phases as well. And then by mass balance, we can calculate the concentration of nitrogen in the fluid. So with these concentrations of nitrogen in different phases defined, that allows us to then define what we call the partition coefficient. It's a way of quantifying the distribution of nitrogen between phases when those two phases are in chemical equilibrium. So I define the partition coefficient for nitrogen in this form here. So we have the concentration of nitrogen in a mineral phase normalized to the concentration of nitrogen in the fluid phase. So mineral over fluid for nitrogen concentration. And I also have, we'll report here soon, magma fluid partition coefficients as well. And for magma fluid partition coefficients, it just replace the mineral with magma. So it's magma over fluid for that partition coefficient. Okay, so we use X-ray spectroscopy to get nitrogen concentration. With nitrogen concentrations, we can define these partition coefficients. Okay, so let's now bring these partition coefficients back into this context of the deep cycling of nitrogen, or the response of nitrogen to the subduction process. If we measure a low nitrogen partition coefficient, that suggests that for that particular condition, pressure, temperature, composition condition, that would promote nitrogen being incorporated into the fluid phase over mineral phases. And recall, it's the fluid phase that exits the slab and ultimately rejoins Earth's atmosphere. So low partition coefficients are associated with nitrogen taking the blue path and staying a part of the atmosphere, whereas high partition coefficients for nitrogen are associated with retention in minerals that make up the slab. And therefore, high partition coefficients are associated with nitrogen being retained in the slab despite fluid loss, drawing nitrogen out of the atmosphere, thinning it over time. So we have kind of our partition coefficients mapped onto kind of the expected kind of behavior of nitrogen within subduction zones. Okay, so here we are. This is our first result. So for any experimental study, the first thing that experimentalists do is they need to know how long they need to run their experiment for to get some amount of chemical reaction or to achieve chemical equilibrium in their system. And so the way you typically do this, the first way to do this is to run a time series where kind of the equilibrium state of a system should be time independent. And so you need to run the experiments long enough so that the partitioning that you measure for that experiment is also time independent. So this is now the partitioning of nitrogen between melt and fluid as a function of experimental duration. What you can see is that for our shortest duration experiments, they have relatively high partition coefficients associated with them. As we go to longer duration experiments, we achieve a steady state, repeated values from about 50 hours to longer durations. So we can just quickly conclude that we have to run experiments for at least 50 hours to achieve an equilibrium distribution between melt and fluid. So this is the first data that are required for us to be confident that our experiments are closely approximating an equilibrium state. Okay, so once we kind of had this time scale defined to achieve equilibrium, we can then start to look at the effects of other parameters on controlling the distribution of nitrogen between different phases. So the first effect we will look at will be the effect of temperature. So for these experiments, we're fixing pressure and redox, and then just varying temperature. So this is the partitioning of nitrogen between melt and fluid, and this is biotite and fluid over inverse temperature. So inverse temperature. So on the left side, these are going to be hot experiments, and on the right side, these are cold experiments. What you can see is that for our melt fluid partitioning experiments, we have a positive correlation, which would suggest that higher temperatures promote nitrogen being incorporated into fluid over melt. And we also have a positive slope relating the partitioning of nitrogen between biotite and fluid in inverse temperature, again suggesting that higher temperature conditions promote nitrogen incorporation into the fluid phase. These results are preliminary because we have relatively few data points to define these trends, and the data are somewhat scattered, and therefore these trends are not significant at the 95% confidence level. So there's preliminary evidence for temperature causing nitrogen to partition into fluids, but we're not 100% confident at this moment. Okay. So then we can then look at the effect of oxygen potential or the redox state of slabs. This is the same form as before, melt fluid partitioning, biotite fluid partitioning versus redox state of the experiment. So this is the redox state of the experiment with respect to the nickel-nickel oxide oxygen buffer. So if the experiment has the same oxygen potential as the nickel-nickel oxide oxygen buffer, it'll have a 0 value here. And if it's more reducing, it'll go in this direction. If it's more oxidizing, it'll go in this direction. So we have oxidized experiments, and we have reduced experiments. And let's just focus in on my cold steel results to start. So a cold steel apparatus is another apparatus that we use to react materials under controlled pressures and temperatures, but it's a lower pressure device that I didn't introduce in this talk yet. But we did do some experiments with a cold steel apparatus. And then we can then fit, I guess, our cold steel experiments with this line here. And what you can see is that our most reduced experiments have the highest partition coefficients associated with them, and our most oxidized experiments for the cold steel have the lowest partition coefficients associated with them as well. And we can compare our results to those reported by Lee et al. In 2015, using also a cold steel as well under similar pressure temperature conditions. You can see that their data are in good agreement with ours, kind of scattering about our correlation line. Okay, and then I can then compare our cold steel results to results from a piston from our piston cylinder experiments too, given by these circles. And we have very similar systematics for our piston cylinder experiments, slightly higher pressure experiments. Again, where our most reduced experiments have the highest partition coefficients associated with them, and our more oxidized experiments have lower partition coefficients associated with them as well. Essentially, we just have parallel trends between our lower pressure and higher pressure experiments, which is foreshadowing that maybe pressure has a large impact on the reactivity of nitrogen, which I will introduce in a couple of slides going forward. We're just kind of foreshadowing the pressure effect right now. And we can then compare our melt fluid partitioning to bi-type fluid partitioning results. You see we get a similar negative trend. Again, our most reduced experiments yield the highest partition coefficients, and our more oxidized experiments yield lower partition coefficients, showing nitrogen's less reactive. And these negative trends all really make sense with the way I've motivated the talk thus far. Recall that under more reducing conditions, when this O2 value is low, that will stabilize this reactive form of nitrogen with respect to this less reactive form of nitrogen. So under these more reducing conditions, we do expect that nitrogen will be more reactive with melt and more reactive with bi-type. And that's manifested in these higher partition coefficients under these more reducing systems. But something that maybe is not as obvious looking at these negative trends is that these slopes are actually quite shallow. We have about a 6 order of magnitude variability in the redox potential of our system. We only have slightly over an order of magnitude variation in nitrogen partitioning. So we have a relatively shallow slope in log-log space. And I interpret this shallow slope to reflect that actually the majority of nitrogen species that we stabilize under these reducing conditions will be the ammonia molecule, which itself is an unreactive form of nitrogen. So these more shallow slopes reflect that only a small component of the reduced nitrogen species will be the mineral reactive form, the ammonium ion, rather than the ammonia molecule. So the slope here, these shallow slopes, are a reflection really of the relative basic conditions, where basic conditions will promote the stability of the ammonia molecule with respect to the ion. And just to emphasize this, this more basic fluid condition is naturally applicable. Our experiments are approximating nature, and we do think that slabs will have relatively basic fluids associated with them, which would promote the stability of this less reactive, reduced form of nitrogen, the ammonia molecule. Okay, and as we foreshadowed, the effective pressure is actually quite significant, and that's given by these plots here. This is melt fluid partitioning, bi-type fluid partitioning, versus pressure normalized to temperature, but we're fixing temperature, and our experiments are essentially at about 1,000 Kelvin. So this really is just changes in pressure. So we have low pressure conditions and high pressure conditions, and this is about 1 GPa, 2 GPa, or 3 GPa pressure, or about, up to this is about 100 kilometers deep into the planet at 3 GPa. You can see that when we go from our low pressure cold seal experiments to the piston cylinder experiments, we get a strong positive correlation between nitrogen partitioning and pressure. And we get that same strong positive effect when we look at bi-type fluid partitioning for nitrogen versus pressure, going from very unreactive nitrogen at low pressure, but by the time we get to about 100 kilometers deep, where pressure is equivalent to 100 kilometers deep within the planet, nitrogen actually has a D value or partition coefficient that's getting very close to 1, or a value in log space of 0. So we have this strong positive effective pressure. What we can do then is we can then take these different significant effects, namely pressure and redox, and then parameterize those effects to yield this equation that allows us now to relate the pressures and temperatures and redox states of slabs to the expected partitioning behavior of nitrogen within those slab environments as well. So that's what I want to do now is take our parameterization and apply that parameterization to the expected pressure, temperature, redox conditions that slabs experience as they subduct. We take the pressure temperature conditions for slabs from Syracuse and others published in 2010. These are just the different slab geotherms that they calculate in their dynamical models. And just want to introduce this figure a little bit. You see we have these kind of sinusoidal curves. So slabs initially mostly subduct under very low temperature conditions, mostly going up in pressure with very little temperature increase. But at about 3 GPa or so, for most slabs at least, they start to encounter the mantle wedge. And that's a very hot component of the subducting system. And therefore, the slabs go from low temperature to high temperature very rapidly as the heat from the mantle wedge floods into the slab. And so over this relatively narrow pressure range, much of the slab dehydration reactions occur, having this narrow pressure range at about 2.5 to 3 GPa. And then once the slab kind of has thoroughly equilibrated a little bit with the mantle wedge, it then starts to increase in pressure again with relatively small amounts of temperature rise. Most slabs that are being subducted today are in what we call a cold geotherm state. So think about kind of the far end of the Pacific Ocean, on the western edge of the Pacific Ocean. For me, at least, that's the far end. And that's a very old lithosphere which is being subducted, so it's very cold. And that kind of those types of slab geotherms kind of are given by these blue lines here. And that cold slab geotherm behavior is contrasted by hot slab geotherms, which are given by this orange line or these different gray lines, which are represented by the Cascadia subduction zone in the modern day, where essentially we're subducting almost zero age lithosphere off the west coast of North America. You see that for hotter slabs, they actually dehydrate under a much lower pressure. So they cross kind of these different dehydration reactions at a much lower pressure compared to their cooler counterparts. So we're going to clue back into this kind of different regimes, hot and cold slabs. And just to emphasize it, this figure is color-coded in gray for the amount of water that's contained within the upper sections of the slab. So kind of shows you where the dehydration reactions are happening as we go from darker grays to lighter grays, the different water contents. Okay, so we'll take these two different end members, kind of the cold end members of the Western Pacific, and then the hot end members of the of Cascadia. We'll use these different PT paths for these different types of subduction zones to make specific predictions for nitrogen partitioning. And these different dash dot lines are these PT ranges where dehydration reactions are being forced very rapidly. So we have large amounts of fluid being lost kind of along these portions of the geotherm. So we're going to clue into those specific PT conditions where those dehydration reactions are most prominent. Okay. So we'll first start out here with the hot geotherm, and applying our parameterization to the hot geotherm predicts these values for bi-type fluid partitioning. You can see that, and this is the punchline of the talk, is that if we have a hot geotherm, and we have oxidizing slab conditions, nickel-nickel oxide +1, so 1 log unit more oxidized than the nickel-nickel oxide oxygen buffer, which is a similar oxygen fugacity to arc magmas kind of globally in an average sense. So this is kind of a FO2 or a Redox potential that we think is applicable to subduction zones. So under these conditions, hot slabs will have very low partition coefficients associated with their fluid loss for nitrogen. So as hot slabs lose fluids, we then predict very efficient expulsion of nitrogen within that slab to the fluid, ultimately rejoining Earth's atmosphere. So hot slabs and oxidized slabs will be the most efficient way to return nitrogen back to Earth's surface. Okay, and then we can then contrast our predictions for hot slabs to those for cold slabs that dehydrate under much higher pressure conditions. And again, because we had that strong positive effect of pressure on nitrogen partitioning, you can see that if cold slabs are reduced, here nickel-nickel oxide -2, so 2 log units more reduced than the nickel-nickel oxide oxygen buffer, we actually predict for the initial dehydration of those cold reduced slabs that nitrogen will have a D value or partition coefficient in excess of 1, showing a preference for the mineral phases over the fluid phase. So very little nitrogen can be expelled from cold reduced slabs, and really you have to have oxidized conditions within cold slabs also to promote these low D values for nitrogen that are associated with the efficient loss of nitrogen from cold subduction zones. So oxidizing conditions are required to efficiently mobilize nitrogen in these cold slab environments. Okay, and so just some speculation. In the modern day, let's see, I'll start, I guess, because the ancient time, Earth over geologic time has cooled off, and with Earth cooling off, or if we go back in time, with Earth cooling off, that predicts that Earth will have faster plate rates in its geological past, and will have, on average, hotter slabs. So it makes sense that kind of ancient subduction on Earth would have been kind of more close to the warm end member that the Cascadia subduction zone provides in the modern day. So the suggestion that warm and oxidized slabs have been crucial in maintaining a nitrogen-rich atmosphere fits with the likely importance of warm subduction zones into the geologic past. In the modern day, much of Earth's subduction is closer to the cold end member of the Marianas. And as the Earth continues to cool off, plate rates slow down and the potential temperature goes lower, we actually would expect dehydration reactions to happen under progressively higher pressures and cooler conditions. And as we've demonstrated, these higher pressure, cooler conditions will lead to actually larger D values for nitrogen, and therefore potentially the greater retention of nitrogen in subducting slabs going into the geologic future. And that may give rise to a thinning of Earth's atmosphere as more and more cool subduction can draw more and more of Earth's nitrogen in its atmosphere into its interior. Okay, so just to then conclude, the major findings of this presentation that we've completed a systematic series of experiments that have defined the behavior of nitrogen in slab systems under applicable pressures and temperatures and compositions. We've identified redox and pressure as having major impacts on nitrogen partitioning between slab minerals and fluids, where more reducing conditions and higher pressure conditions will both make nitrogen more easily retained in a slab despite fluid loss. And therefore, we suggest then that the ancient subduction of oxidized and hot plates, that may be key in the maintenance of the nitrogen-rich atmosphere that this planet has enjoyed over the billion-year timescale. So thank you very much for your attention. And if there are questions, I'd be happy to answer them.
Okay, thank you, Colin, for giving the presentation, giving the talk. And now it's time for questions. And for the audience, if you would like to ask a question, feel free to open your mic. And before you ask a question, please let us know your name and your institution. You could also type in the chat, and I could read the question for you.
Oops, excuse me.
Okay, I could read one question from Li Jilei from Institute of Geology and Geophysics, Chinese Academy of Sciences. And it says, hi, Colin, very nice talk. If we want to testify your study from natural samples, what kind of high pressure rocks or minerals should we look for? It seems that it is usually white mica rather than biotite in the high pressure alkalized.
Yeah. Yeah, that's a great question. So there has been work on actually measuring the distribution of nitrogen in materials related to subduction. Maybe slab lithologies that have been exhumed back to Earth's surface. And I think can I go to it? Let's see. Yeah, I guess this is the slide that I guess. It actually supports this basic idea that that the slab geotherm environment may be very crucial in controlling the behavior of nitrogen. And so this is now looking at subduction zone rocks that have been, or slab rocks that have been exhumed in the Alps of Europe. And let's see, without kind of going into the details of this paper, they basically are able to use correlations between these different fluid mobile elements to argue that minimal amounts of devolatilization have occurred for these slab lithologies, and they find that as suggested here, that much of the nitrogen is associated with micas in the various forms. It is true that white mica is also a very important mineral for subduction systems, as the question suggests. And there have been papers that have come out recently that have also looked at nitrogen partitioning between white mica and fluid, and it also appears to be a very strong control that white mica has when present in a chemical system. But essentially, what this paper shows is that natural settings, nitrogen's behavior is being modulated potentially by the slab geotherm environment, where colder environments lead to large amounts of retention of nitrogen and other fluid mobile elements as well. So here's nitrogen correlating with cesium, and they would predict kind of a decorrelation of these elements if large amounts of devolatilization occurred. And so this slab cold environment is associated with nitrogen retention as supported by our experimental results as well. I'm not sure if I fully answered that question or not, but I'd be happy to expand further if they're interested.
Okay, next question, please.
Hey, Colin.
Hey.
Can you hear me?
I can.
Hey,
yeah.
Nice to meet you. Yeah. Okay, cool. It's a very interesting talk. So.
Thank you.
Yeah, I have one question for the figure. It shows, shows the partial pressure of the nitrogen as a function of the Earth's age.
Yep. Yeah. I can get to that.
This is very interesting to me, the figure. I mean, where did you find? I mean, which article do you use to find this figure, or which kind of literature data you used for that?
I just pulled. I cited it in the beginning. So so SOM, they have a paper in 2016 where they measure the diameter of fossilized raindrop imprints. Marti 2013 measurements of the chemistry of fluid inclusions that they think equilibrated with Earth's ancient atmosphere 3 to 3.5 billion years ago, and then Bernard 2006 using NC ratios for organic material. So I was able to pull together kind of these different studies that had kind of made some estimate for either the total pressure of the atmosphere or specifically the nitrogen P and 2, and then kind of put this plot together. So this is not in any paper that I'm aware of. This is just my own creation for this talk.
Okay, it's a very cool figure. I'm thinking it's because around the age shows like around 2.6 billion years. Then it's exactly the great oxygen event, right? Yep. So which means the oxygen is definitely, oxidation situation is very, play important role to affect the partition of nitrogen between the minerals and the melt or the fluids. So it's kind of, interests me about the oxygen come from the interior of the Earth. It's not like the oxygen, just produced by the photosynthesis. What do you think?
The source for the oxygen associated with the GOE, you're asking me?
Yeah.
I mean, that's a huge question of, what ultimately drove, I guess that, I mean, it's still not that much oxygen in the atmosphere in terms of a partial pressure at that moment, but, the major rise in oxygen partial pressure happens, only 500 million years ago. So yeah, I don't have a strong opinion on, exactly what transpired at the GOE to kind of have the first rise in the oxygen potential of the atmosphere. Yeah, I mean, it very well could be related to, changes in, I guess, the way that materials were being cycled between Earth's interior and Earth's exterior. I guess in the ability for the Earth to, sequester, reduced carbon, keeping it, kind of isolated from O2? It's a huge question. Yeah, I don't have a strong opinion on it.
So yeah, if I'm thinking if the oxygen just produced from the surface on the Earth, so they will not exactly affect the partition of the nitrogen between the mineral and or the magma or the fluid interiors of the Earth. So it turns to the oxygen from the interior of the Earth and can directly affect the nitrogen partition and then to let the nitrogen released from the interior of the Earth.
Oh, so you're thinking kind of prior to the GOE, you're wondering about would slabs,
so I'm wondering
would slabs themselves have also been more reduced? Like you're asking me what controls the redox state of the slab that's being subducted down, or?
I mean, just like the oxygen, if it can just directly come from the surface on the Earth, I mean, it will not exactly affect the partition of the nitrogen between the mineral and the fluid interior of the Earth.
Yeah.
So which means the oxygen from the interior of the Earth.
I guess.
Do you understand it correctly?
Maybe. I think the oxygen at Earth's surface could affect the partitioning of nitrogen in slab environments because it's very possible that that if the surface of the planet is oxidized and the sediments that accumulate on the tops of slabs will also then be more oxidized as well in response to that oxidized atmosphere. Then those oxidized materials will get subducted into the into Earth's interior, and then help to modulate the oxygen fugacity that's present as those dehydration reactions occur.
Okay.
I think it's an open question though. Whether even in the absence of an oxidizing atmosphere, would, for example, serpentinization of the slab also lead to kind of internal oxidation of the slab as well? So that maybe even in the absence of an oxidized atmosphere, slabs also might be oxidized themselves. So yeah, you could have multiple different reasons for why slabs would be oxidized. Maybe one related to the oxidation of the atmosphere, and then another one related to kind of the internal chemistry of the slab itself being predisposed to becoming more oxidized as serpentinization progresses too. So yeah, I think that the redox state of slabs through time, I think, is a major open question regarding the deep cycling of materials between Earth's surface and Earth's interior on the billion-year time scale, kind of in the face of the GOE, in the face of the second rise of oxygen too.
Okay, thank you. Yeah, we'll try to save some time for other people's questions.
Okay,
thanks.
Okay. Hopefully I was able to answer your question. Yeah.
Yeah, exactly. Yeah.
Okay, next question, please. Okay. Dr. Chen Lanfei has one question and is asking, he may have missed some part of your talk, but how did you determine the nitrogen content in a quenched fluid and melt?
Yeah.
And Dr. Lanfei is from the Institute of Deep Sea Science Engineering, Chinese Academy of Sciences.
Okay. Yeah. So we had a high enough concentration. So we doped our experiments with nitrogen. So we had high enough concentrations of nitrogen in our experiment that we could analyze the nitrogen content of the quenched magma and the minerals using an electron microprobe, which is essentially X-ray spectroscopy. We didn't actually directly analyze the nitrogen content of fluid. We designed our experiments so that we could do mass balance calculations to determine the nitrogen content of the fluid. Essentially what we did is we had large amounts of fluid and small amounts of magma and minerals in our experiment. So that made then the fluid the overwhelmingly major reservoir for nitrogen in our experiments. And therefore, if we know the bulk concentration of nitrogen in our experiments because of our doping levels, then we can also use that information to place a relatively tight constraint using mass balance on the fluid chemistry. So between X-ray analysis of the quenched melt and minerals, and mass balance, that allowed us to do the full determination of nitrogen's distribution in our experiments.
Okay, next question, please. Actually, I have a quick question. Just on this slide that you have been showing,
this is a popular slide, huh? Yeah.
For this plot, I'm curious. Did the people that try one consistent method in estimate the nitrogen partial pressure in the atmosphere? Because I bet that each method, by themselves, represents, let's say, different approach to evaluate the nitrogen partial pressure. For example, that we have more fluid inclusions chemistry data trapped in the hydrothermal cores in different parts of Earth history, so that we could compare everything using the same bar.
I'm not aware of one study that's been kind of systematic through time using one method to constrain the partial pressure of N2. I would have to assume that the method that Marti used, where he basically analyzes fluid inclusions that were trapped, kind of at a specific portion of Earth's history, that method could be, expanded to, capture, kind of constraints for the nitrogen partial pressure over a wider range than what they reported in this paper here. So I imagine that this approach could be more universally applicable. I'm not familiar with, I guess you have to have samples that you convinced yourself that the fluid inclusions within those samples did equilibrate with the atmosphere, and then you also had a firm age constraint on when those fluid inclusions were formed. But if you had those two bits of information for a rock, then I presume you could use that material to place more constraints in this space as a function of time. So yeah, I mean that would be a very impactful study if a group did take that on in a systematic way, I think.
Okay, do we have one more question from the audience? Okay, so here is Deng Zheng from Institute of Geology and Geophysics, Chinese Academy of Sciences. And hi, Colin, thanks for your talk. Do you think the cold subduction zone is more oxidized than hot subduction zone?
It could be. It could be. I mean, so this is a basic question, like what controls the redox state of a slab? It's a major question, but so I mentioned before, one possible controlling reaction would be the serpentinization of the slab prior to its subduction. So associated with serpentinization of the slab is the production of magnetite. So the production of iron in a relatively oxidized state. And so a slab that has had more serpentinization should have more magnetite, and therefore potentially should be a more oxidized slab. And then the question is, well, what controls the amount of serpentinization of a slab? And I think that might correlate with its thermal state. The colder a slab is, kind of the more of that slab could potentially be cool enough to be serpentinized. So there is the potential then, for colder slabs being more oxidized because of that greater propensity for serpentinization. That's speculation though. I'm not sure if that has been if that connection has been drawn in any kind of quantitative way. So so it's possible, but maybe it's not certain that there's a relationship between slab thermal state and slab oxidation state. It's a great question.
Okay, so we ran our seminar for 60 minutes sharp. So thank you very much, Colin, for giving the talk, and thanks everybody for participating. And 3 days from now, we are going to have another second talk. Dr. Qing Zhicheng from SysTech China is going to talk about the carbonated melt physical qualities. So with that, we wrap it up. And thank you, Colin, and thanks everybody. And have a good day and have a good evening, Colin.
Thank you very much, for the opportunity. I enjoyed this presentation. It's fun to get questions from so many different people from different groups. So thank you.
Okay, thank you, everybody. Have a good day. Bye-bye.